amplifier integrate the input signal is the poor dynamic range, which makes it good for applications where we want or we need very high sensitivity, but we don't really care about the dynamic range of the receiver is not a matter. We don't need to receive very high signals. Okay, so just one point I want to make sure that it's clear for you. You remember earlier here, we have seen that the bandwidth is 1/2 by CTRL. Even if we decrease C to a very, very small value, still the bandwidth, and having a large R, still the bandwidth will not be good enough. Let's do an example just to see why are we doing all of this, why not just decreasing the C will be enough to solve the problem. Okay, so for the high impedance now, sorry, I forgot my point. So for this high impedance, we said we want to have a very high bias resistance and a very high input resistance for the amplifier. So if we can increase them, or we can increase them up to 1. So let's say we have R total of 1 mega ohm. Okay, and we use a very small capacitor. Let's say that CTL, or the capacitance we have is 1 picofarad. So let's try to calculate the bandwidth that we need. And if you do the calculations, I've done the calculations, as I remember, it's not a mistake, it's 160 kilohertz. So you can see it's very small, although we have considered a very small capacitance. Okay, so you can see that increasing the resistance while decreasing the capacitance will not solve the problem. Still, we have a very limited bandwidth. So that's why we go for such an architecture, such a structure where we need to introduce equalization and sacrifice the dynamic range of the receiver. Is it clear?
Just a simple question. How would the equalizer give us more band, or provide us with a reasonable
It will
bandwidth?
compensate. That's why it will compensate for the response of the system. This is the system. This is what you will have out of the amplifier.
Okay.
So we will need an inverse response. So here we amplify more signals of lower frequency. Here we do the opposite. So that's why we will end up with equal.
Okay, throughout the whole frequency.
Yes.
Okay. Thank you.
Okay, so now the third receiver structure, the transimpedance front end. Transimpedance front end overcomes the drawbacks of the high impedance, which are the need for equalization first, and the limited dynamic range. How does it do that? By using a high transimpedance, a high impedance amplifier with a negative feedback. So how will this work, or how will this reduce the how would that reduce the noise without reducing the bandwidth? We'll see now. First, the name transimpedance comes from the fact that it's a transimpedance amplifier, where we have the input is a current, the I detector, and the output is a voltage. So that's why we call it transimpedance. So as we have seen, it's the effective resistance or the effective impedance in the input of the amplifier is what determines the bandwidth for us and the noise. Okay. So we need for this architecture, for this structure, to calculate what is the effective impedance in this case. So first, let's consider the open loop system, the open loop transfer function. The output over the input. This will give us the impedance. Voltage over current will give us resistance. So that's why we want to get the current to voltage transfer ratio. So first, let's draw our architecture and see how it will work. Okay, set up without the feedback, the negative feedback resistance.
And there a current source?
This is the detector, the current from the detector. Total capacitance, total resistance, the amplifier itself, then the output voltage, and here is the input voltage. Okay, so what we want to calculate is V out over I detector. I in the I detector. Okay. And we know that V out again is G. Here the open loop gain is G. So Vn is what? This is IDT, the detector current. We can So the Vn is the I detector multiplied by the total impedance here, the resistor, total resistor in parallel with the total capacitance. This will give us Vn. We can see that. Okay. Are you following up to here? So I have just added these in parallel. Okay. So the open loop gain is and if this is Vn, so then we can do minus G Can you see what I have done here? So, okay, the bandwidth is determined by the imaginary part here, RTL and TTL, which is the same as we had for the other structures. So still here, we can say that the bandwidth is equal to this is the derivation of this. Okay? I'll give it back in a minute. Can you see, or should I switch it off? So what we have seen here, that without the feedback resistor, we are still the same bandwidth determined by RTL and CTL. Okay. So now we want to see what will happen if we have the feedback.
So, wait a second.
What's VA? Inverse VA, or is that the?
Yeah, this is the unit.
Unit.
Because it's voltage over current.
Oh.
Maybe use the other one.
But I wanted to come over the other way. Okay?
One more second. Okay. Thank you.
So now for closed loop. First, let's figure out how will the current flow here. So, which is higher, V out or V in? Obviously, which is higher? V out. This is an amplifier. Okay. So then, because V out is higher than V in, the current will flow in this direction, and we have the detector current coming in this direction. So in this case, the total current will be the I detector plus the current through the RF. Okay. So then we have I detector plus the current through RF, which will be V out minus V in over RF. They will these both will add together and will flow through RTL and CTL. Okay, and the current through RTL, CTL can be given as V in over RTL, CTL. Voltage over resistance. Okay, so let's try to calculate this, and we have already done that in the previous part, and if you remember, we ended up with okay, we know so let's now try to rearrange things to have IDT, the detector current by itself. Just replace V minus V in with V out over G. There was a minus here. Okay. So all of this is over R. Right? And on this side, we can replace the V in by also V out over G, and then we can rearrange it from these. We can rearrange things
V output plus V output G is the plus
Where? Where?
term VO plus VO, this one, yeah,
Yes.
plus.
Yes. It was a minus, but we have V out is equal to minus G V in.
And what's the name of the current in the drawing on top left? current of detector.
Yes, detector, DT.
Okay.
Okay, so we were. So now let's have I dt on one side, and on the other side we can have So what we have done here, we want IDT at one side by itself, and we have rearranged the other terms, and we ended up with this. RF RF is usually chosen to be much lower than RTL. Okay, and we know also G is a very high number, very large gain. So according to that, compared to the 1 over RF, this can be 0 and this can be 0. These will be very small numbers because RTL and the G are very large numbers, and here also the G is very large, making 1 over GRF almost 0 compared to the 1 over RF. Okay. So we'll end up with this. IDT over VO is equal to this. You just rearrange things minus this. But what we really want is VO over IDT. So let's from here to here. This is the closed loop transfer function. Compared to the one we just obtained for the open loop, we can see that now G appears in the imaginary part. Okay. Then from here, okay, is this good or bad to have this G? Why it's good?
It is values. Because if the values is not anymore, we have just called
Yes. Yeah.
we can change the gain, so we can keep the value.
Yes. So we can increase G while keeping RF high. So we'll end up with a good bandwidth, high bandwidth, and a low thermal noise, which means a high sensitivity. Okay, however, we cannot really keep increasing G and increasing RF forever, because this will result in issues with the stability of the amplifier. That's why this structure will result in a lower sensitivity than the sensitivity that we can obtain with the high impedance. In the high impedance, we were free to increase the R, okay, and compensate for that with equalization. However, here, because of the stability issues, we cannot really continue increasing the R, the RF. Okay, that's why the sensitivity for this structure is lower than the sensitivity we obtain with the high impedance. However, we have solved the problem of the high of the limited dynamic range. So then it's a trade-off depending on your application. If sensitivity is more important for you, then go for the high impedance. If the dynamic range is more important for you, then you can go for the transimpedance structure. Okay? Okay.
So, do we need to draw something like this in the exam?
Mm-hmm.
Do we need to draw something like this in the exam, or is it that given more you can learn by heart? So it's like, I understand the map, but I couldn't draw the to know about this amplifier thing.
Okay, because
The
yeah,
circuit.
you will need to have some background on operation amplifiers. So
Okay. So I should be able to draw this.
yes.
Okay.
Can you just explain the step between IGT plus VD, and then what happened to the other step?
Which step? This one?
No, the line above.
Uh-huh.
What happened between these two steps? This step
This
and-
one and this
yeah.
one. So it's just rearranging things.
Where did the IVT
Sorry, what is this? There's something wrong here. No. Okay, so what we did, yes, we have just arranged things. So this is IDT as it is, V out as it is, V in,
Okay.
replaced by
VO.
minus VO over G.
Yeah.
You know that, okay? And on this side, also V in replaced by minus VO over G. Okay? And here, it's the same. Then we go, move everything to the other side and keep IDT by itself. And just rearrange things here. So we'll end up with these four terms. We want them individually because we wanted to show that this is almost zero, this is almost zero compared to 1 over
Okay,
I.
so where did IVT go? It goes
IDT is here.
Okay, so it's on the other side.
Yes.
Okay, yeah, I understand.
So from this equation, we go to this equation, and then we come to this, then that.
Okay. So that one should be IVT is equal to VO.
Yes.
Okay.
Is it clear, or the way I have written things is a bit confusing? Okay.
So the goal was to put the B, put G into the top range.
Yes.
Close the goal.
Yes, here. So when we have done all of that, we found that now we have G, this G at the top, which will solve the problem for us. We can increase G to compensate the increase in R. Okay. Okay, so far we have seen that the performance of optical communication networks, and when I say performance, I mean the ability to correctly recover symptoms for digital systems. This performance, we have seen that it's mainly determined by two or affected by two impairments. Intersimple interference, which results from dispersion, as we have discussed before, and intersimple interference can be reduced by quantization, equalization. Why have written quantization? Sorry, I'm mixing the two modules together. Equalization. Please replace it. It's not quantization, it's equalization. I'm doing the other module for digital media engineering, where we keep saying quantization, so I'll written quantization here. Okay. Make sure you replace it. So yeah, intersimple interference is reduced through equalization. So similar to what we have seen here, the equalization will be a shaping filter with a frequency response that is inverse to the frequency response of the system to compensate for any distortion in the system. The other thing is noise coming from different noise sources. We have studied thermal, dark current, quantum noise. And why is this noise important for us? Because when we receive the signal, by the time the signal arrives at the receiver, it will be attenuated. And this noise can be reduced through filtering. And it was found that a bandwidth, or a filter with a bandwidth of 0.7, the bit rate will give us a good compromise between limiting the noise but not introducing too much intersimple interference, because when we limit the bandwidth, this means that the simples will come closer, the interval between simples will be smaller, which will increase the intersimple interference. They found that a filter with 0.7, the bit rate will result in a good compromise between the two, limiting the noise and not introducing too much intersimple interference. During the rest of this lecture, we will be evaluating the impact of noise on baseband system. You might be asking, so what have we done 2 lectures ago when we established the quantum limit, the minimum energy we need to detect, the minimum energy we need to receive in order to detect the simple without error. The difference is, or why are we doing this again? When we established the quantum limit, we were only considering quantum noise. Now, today we will look at, or we will include all the noise sources. So let's first agree on the assumptions that we have. According to the central limit theorem, the sum of different independent random variables with different distributions will converge into a Gaussian distribution. So regardless of what the distribution of these random variables, when you add them up, they will converge into a Gaussian distribution. Okay, so this is the Gaussian distribution with a zero mean. And also we have seen that the different noise sources we have considered, they are all additive white noise, which means that they do not depend on frequency. They have constant power spectral density. Okay, remember all the formulas we had, Nyquist, Schottky, they didn't have frequency. So all the noise we have considered is not a function of frequency. So at the receiver, the receiver will sample the incoming signal at regular intervals and will need to make a decision whether it's a 0 or a 1. However, this decision will not be easy because noise will reduce the difference between a 0 and 1. We'll have a threshold level or a decision level where if the signal is lower than that level, then it's 0. If it's higher than that level, then it's a 1. But because of the additive noise, we can see that we can have a 0, that the noise will cross the threshold. So it can be at the sampling instant, for example here, then it will be detected as a 1. And we call this error a false alarm. So it's a 0, but we detected a 1 as a result of the noise. Okay? And we might also, here, or we might also have a 1, and because the signal is impaired now with noise, it will go below the threshold. So imagine this goes below this threshold. So then a 1 will be detected as a 0. And we refer to this as erasure error. So 1 was erased. Okay? So these are the 2 types of errors that you can encounter in our system. So we have read that the noise will have a Gaussian distribution. So around the 0 level and the 1 level, we will have a Gaussian distribution, as we can see here in the figure. So if this is the 0 level and this is the 1 level, so we'll have Gaussian distribution around each of them. So just to make it clear for you that, so we have this unipolar signal, has 2 levels as we said, 1 and 0. And we said we'll have additive noise. Okay, and then we'll have our threshold D. So if this is the 1 level, and this is the 0 level, we will have a Gaussian distribution Can you see that? So this is the 1 level, this is the 0 level, and this is the distribution of the noise added together. And this is what you can see. So this is the detection level, the threshold level, and we can see it's A1, the 1 level, minus A0 over 2 plus A0. This is A0 and this is A1, so the D in the middle between them will be given as this, and which is A1 plus A0 over 2. Okay? So we said the 2 types of errors we have. The false alarm, T error 0, and the erasure error P, the error of 1. Okay, so what is the probability of each error from the figure here? You can obtain the probability of the error 0 by integrating the curve over this area between D to infinity. And for the other error, will be the other way around. And this is what we have here. So probability of error 0, which is the probability of V higher than the threshold, is given as the integration of the distribution from D to infinity, and the probability of error 1 is the integration from minus infinity to D for the distribution around A1, the one level. Generally, that these two distributions are assumed to be asymmetric, so these are the same, and asymmetric with the same variance, which will make P probability of error 0 equals to probability of error 1. The average probability of the system, we said the two errors, or we find the two errors in the system. So the average probability will be the probability of error 1 multiplied by the probability of sending 1 plus the probability of error 0 multiplied by the probability of sending a 0. And if we assume an ideal signaling, binary signaling system, this will make P1 and P0 equals to, we have discussed this before. Yes. Okay, an ideal binary signaling system where we have both the 1 and 0 are transmitted with the same probability. Okay. So, given that this is 0.5 and this is 0.5 and these two are equal, then the probability of error in the system is equal to the probability of 1 or equal also to the probability of 0. You can see that. Okay, so now we said our distribution is a Gaussian distribution, and for us here, if you want to consider A0 not to equal 0, so as I have shown here, if we said this is the 0, we say this is 0. So then A, and this is A0, and this is A1. So A0 is not equal to 0. So we have to have the Gaussian distribution where the mean is not equal to 0, as you can see here. And now we try to do the integration. We put the distribution. And to simplify things, we make B minus A not sigma root 2 is equal to x, which will make dx is equal to dv over sigma root 2. And if we use this, substitute in the upper equation, we will end up with this equation. And you know, or you should know, that this function, what do we call it? The complementary error function. We must have studied this before, I'm sure. Anyone who has done communication before must have seen this before.
I can communication, but I haven't seen it.
I'm really surprised. Okay, so this is the complementary error function. Integration from u to infinity e to the power minus x2 squared 2 over pi. So this is the complementary error function of u. So we can replace this integration with the complementary error function, as you can see here. So here u for us will be the d minus a naught sigma root 2. And this is how we can obtain the error, the probability of error given the level or the current at A0 and the variance of the Gaussian distribution. A good approximation, you might ask now, okay, what can I do with this complementary error function? A good approximation of the complementary error function is what you can see here. So the complementary error function of x is equal to e to the power minus x squared x root by. And this approximation is valid for all x greater than 3, which is true for us here. So if we said d is equal to a1 plus a0 over 2, so if we replace d with that, we will get a1 minus a0 over 2 sigma delta root 2. So what does that mean? Remember this? Or you can write it down. And we said we can approximate the complementary error function by e to the power minus here would be a1 minus a0 over 2 squared over again the whole thing. So if you were given A1 and A0 and the variance of the Gaussian distribution, you can give us the bit error rate using this formula. So what does that mean in terms of the values that we should use for A1 and A0 and sigma and so on? If we want to have a high, or we want to reduce the bit error rate, what should we do with the A1 and A0? Or what should we do with the difference between them? This is what we have here, A1 minus A0. Obviously, if we given a certain variance, if we want to reduce the bit error rate, then we should increase the difference between A1 and A0. And this makes sense because we have seen here that this is 1 and 0, and when we have the noise, the error will occur when the noise crosses the threshold. So if we have a higher difference between them, then the probability of the noise crossing this threshold will be reduced. And this is what we mean by reducing the bit error rate. Okay? This is a quick example, but I will leave it to you, and I will go through it first thing in the next lecture. And there is also an example from the previous part for the transmitters. We will also do it next lecture. But let's now look at this, the receiver sensitivity. Okay. You know, we talked about quantum efficiency, and we said, what is quantum efficiency?
Minimum limit.
Photons divided by rate of.
Yeah, what you are talking about the quantum limit.
Yeah.
I want the quantum efficiency. So,
Rate of photons divided by rate of electrons, or the other way.
no, the other way.
The other way,
Yeah. Because what we really want is the electron. the receiver, take photons and produce electrons. So this is the quantum efficiency. Another important parameter of the receiver is the responsivity. Responsivity and quantum efficiency, they are basically describing the same thing. Responsivity is the ratio between the detector current and the incident power. So it's the same thing. This is electrons coming out of the detectors, and this is photons coming into the detector. So they're basically describing the same thing, but with different ways. Okay. The quantum efficiency is usually used to describe a detector, a device. And if you go back to the problems we have solved 2 lectures ago, you will see that when we talk about a detector and we say it has quantum efficiency of so and so. Okay? But when we talk about the whole system, the receiver, we will talk in terms of responsivity. Because responsivity gives us values that we understand at the level of the system, at the level of the circuit. Current and power. Can you see the difference? So this is amps and this is watts. Okay? So you will find in questions where we want to consider the whole receiver, or when they want to talk about the whole receiver, they use responsivity. While for detector, we use quantum efficiency. Okay? Yes, so this is responsivity. Okay, actually this is depends on the previous example to understand what is it, and I'm afraid we don't have the time. So next lecture we will do the example and we will continue with this discussion. But just keep in mind the difference between responsivity and quantum efficiency. Okay? Thank you very much. Any questions? Someone wants to ask something?